Hello, 132 students, welcome back. I need to finish up what we weren't able to get done in class today. This lecture is specifically on first law tables, and so if you've already had first law tables, meaning you were in class or in lab on Tuesday, this is just a review. It's not required, but for those of you who have a Thursday lab, this is something that we did not cover in today's lecture that I wanted to go ahead and cover in a video. So the topic, as I mentioned, is first law tables. And first law tables are used for evaluating thermodynamic cycles, meaning we have something on a process or a series of processes on our PV diagram that starts at some initial state and then transverses to different states through different thermodynamic processes. It's supposed to be a curve. Let me try that again. And we have state 1 and state 2 and state 3, but what makes it a cycle is we get back to where we started from. And this guy goes around the PV diagram like this. And so a couple of things to note about thermodynamic cycles. First of all, if we want to create a functional device like a steam locomotive, for example, you want it to be able to run for an arbitrary length of time. So you can't just have it, complete some sequence of processes and then stop. You want it to be able to continuously run, so you need a cycle in order to do that, something that you can repeat over and over again. And I want to analyze or break down a couple of pieces of this cycle. We have one process in which the volume increases from 1 to 2 here, and then a process where the volume doesn't change from 2 to 3, and then a process where the volume decreases from 3 to 1. Which of these processes would you identify as being the expansion work? Well, expanding is when the volume increases, so I would say this is the integral under this segment of the curve is the expansion work. And in terms of the work done by the gas, which is what we've given the symbol W, we have W is less than 0 for expansion work, meaning we're not smashing the gas, but it's doing work on its environment. And then we have another non-zero work segment, and that's the segment from 1 to 3, and it has a magnitude, which is the area under its curve, which is just from the segmented portion and below this region right here. And so the compression work then would be the work from 3 to 1 is compression. And during the compression work, we are doing work on the gas, so this is going to be the magnitude, or the sign of the work is greater than 0. It's kind of a terrible yellow color. I'm going to tune that up a little bit. Great. And so in this particular process, we have that the magnitude of the expansion work, exceeds that of the compression work. In other words, we're getting more work out in this 1 to 2 process than work that we have to put in 3 to 1. And a cycle that has more expansion work than compression work, you get more work out of it than you put into it, that is called a heat engine. So heat engine is a thermodynamic cycle that has a net work output, meaning over the course of the process, the expansion work is greater than the compression work. Let's take a look at this same cycle, and if it were to be same cycle here, we have our 3 points. But in this case, I want to consider the situation where we go in this direction instead, counterclockwise. 1, 2, 3. So all the other points are the same, but now we are traversing the PV diagram in the opposite sequence. And when this is the case, then now our compression work up here from 3 to 1 exceeds the value of the expansion work, which is from 1 to 2. So this would not be a heat engine. Not a heat engine. You got to put more work into it than you get out. Does anybody know what we call this device we put work into? More work into than we get out? This is an example of a refrigerator. I think somebody called it a cold engine in another class, which I think is kind of a funny play on words, heat engine and cold engine, but this is not a heat engine. And so any process that is a clockwise loop, has a clockwise sequence on the PV diagram, is going to be a heat engine. And just to remind you that typically when we talk about work, ordinary W, the simple W, is the work done on the gas. So if we have a net work output, the gas is doing more work than we're doing on it. So in other words, the sum of the work is going to be less than 0 for a clockwise cycle. And a counterclockwise cycle is not going to be a heat engine. We have to put more work into it than we get out. All right. I guess the last bit is that if we wanted to calculate just the magnitude of that work output, whether or not it's clockwise or counterclockwise, I guess the net work of a process, if we just have some process, I guess I can just, I'll make it more arbitrary looking than that. If we have some process that, goes like, some crazy sequence, when we, the net work done or produced during this process, done on the gas or by the gas, is always going to be the area enclosed by the loop. All right, that is all I wanted to say about cycles for now. We will revisit this topic of cycles on Friday, but that was the comments, the sort of preamble or the prerequisite for the main discussion today, which is on which is on first law tables, which we will use to analyze these types of cycles. So let's talk about first law tables, what they are and how we complete them. So as a reminder, the first law of thermodynamics, as we introduced, is equal to delta E thermal, or the change in the thermal energy, comes from two sources: any heat that is exchanged with the system and any work that we do on the gas, or that the gas does on its environment, is going to cause a change in the thermal energy. It's these two inputs and outputs, and this is the effect that it has. This is the first law for an ideal gas. And so what we want to do then is we're going to use this to analyze cycles. And I actually have an example here that I wanted to work through. So let's just jump to the example here. So here's an example of a thermodynamic cycle. It is going clockwise in orientation. So we're going to have net work output, or the sum of the work around the loop is going to be 0. And we have 120 milligrams of helium that are completing this cycle. We have some given information here. It looks like I have one piece of missing information. Yeah, it's 133 degrees Celsius at 0.1. So let me go ahead and add that. Very good. And so we want to complete a first law table for this particular cycle. And so let me show you what that looks like. So the first law table begins with writing down the first law of thermodynamics. And so I like to write it for our table as being Q plus W equals delta E thermal. And these are the column headings for our table. So I'm going to go ahead and draw some lines to separate these things. We have an extra row up front here, and this is going to be the various steps in our process. So you don't want to write down states 1, 2, 3, but we want to write down processes. So this is going to be 1 to 2, this is going to be 2 to 3, this is going to be 3 to 1, and this bottom we're going to call net or sum. Great, so this is the first law table that we want to complete. We want to calculate or determine what the Q and the W and the delta E thermal is for each of these processes as we go around our cycle. Now, so let's go ahead and do that. And I have a strategy that I would like to outline for completing these. And so it's a multi-step process. And so let's outline what that strategy is going to be. Didn't give myself quite enough room here, but that's okay. All right. Starting with step 1. Step 1 is going to be to look at this process and decide if we can identify any zeros in the table. Okay, so can we identify any zeros in this chart? I usually like to start with the work because the work is almost always the most straightforward of the columns or quantities in these problems. And so is there any steps in which the work is 0? Well, 1 to 3 has a non-zero area, and 2 to 3 has a non-zero area. Excuse me, 3 to 1 has a non-zero area, and 2 to 3 has a non-zero area. But 1 to 2 is a vertical line, and that's an isochoric process, which means there's no work done from 1 to 2. So we can go ahead and drop a 0 in there. And are there any other zeros? Well, we have work going on in all of the others. And then from 2 to 3, that's an isothermal process. The change in the thermal energy is the temperature in different units for an ideal gas. So if there's no change in temperature, there's no change in thermal energy. So from 2 to 3, we get a 0 for the thermal energy, or the change in the thermal energy. All right, the last bit here is there's one that we get in every first law table. And if we take a look at this, we think about this, if delta E thermal represents the change in temperature, we have some temperature at 1 and some temperature at 2. It keeps that same temperature when it goes to 3, and then we're back to that temperature at 1, 130 degrees Celsius, 33 degrees Celsius specifically. So the change in the temperature as we go from 1 back to 1 is got to be 0 because it's the same state. And so the change in temperature around a loop is always 0. So we get a 0 down here for the sum of the thermal energy around the loop. All right, the next thing that we want to do is identify the signs for everything that we can. This is going to get you partial credit on an exam, and it's going to keep you from making mistakes. It's just a good place to do the analysis next. So, and actually, I'll keep moving my color coding here. I'm going to go ahead and make my zeros be turquoise, just so they match, because why not? Great. So, signs. What do we got for signs? Well, take a look at our processes here. Well, let's do the work first. The work is almost always easiest to do first. So, what is the sign of the work? Well, from 1 to 2, it's 0. From 2 to 3, we have to ask ourselves the question, are we smashing the gas? And from 2 to 3, the gas is not being smashed. Instead, the gas is expanding. And so we're not putting energy into it. Instead, it is putting energy out there into its environment through work. And so from 2 to 3, we have negative work. So I'm going to go ahead and put a minus sign down here in the corner. From 3 to 1, Are we smashing the gas? Yeah, we go from some big value V3 to some smaller value V1. And so this is a positive work contribution. And we know that it's a clockwise cycle, so that means that the net work that we're going to have done as we go around the cycle, we get more work out than we put in, so the gas is losing energy through work overall, so that's a negative net work around the loop. All right, let's do delta E thermal next. So where do we have, how is our temperature changing? Now, one of the things I like to do when analyzing the temperature is to always think about the isotherms that pass through each point. Each point has an isotherm that passes through it, so 1 has one, goes along like this, 2's is drawn there, but this is family of hyperbola that go along and increasing in temperature as you move away from the origin. So we have state 1 here, which is going to be at a lower temperature than state 2 and 3, which happen to lie on the same isotherm. So that means, how's delta E thermal changing? Well, as we go from 1 to 2, we're increasing, going from the lower isotherm to the upper isotherm, so that's a plus. And, oh, I guess purple is what I chose for the signs. Go ahead and switch that back to purple. And for 3 to 1, we got to get back to where we started, so that is going to be a minus. Q is a little tricky, and we can work through Q if we like, but we can conclude some things just from the sign convention. So if we have a net positive on the right-hand side here, and we're adding 0 to something, well, we must have a positive Q from 1 to 2. And something plus a negative quantity equals 0, well, this has also got to be a positive from 2 to 3. And here we have some quantity plus a positive quantity is equal to a negative quantity. Well, that's got to be negative. So we were able to get the signs for all of these. Like I said, it's worth a lot of partial credit. It's a good idea to do that. I'm going to go ahead and draw an X here through, that's a terrible green. I'm trying to get some colors here that I like, but that is not one of them. How about maybe here? That's better. All right, so we're going to draw an X through the sum of the Q's. That's going to keep you from getting into trouble as we get into the very last topic, which is on thermodynamic efficiency. And it's not a very useful quantity. So I encourage you to put an X in there to avoid mistake. All right, that was step 2. We wanted to identify the signs. And step 3 is going to be we're going to calculate the easy work. By easy, I mean anything that can be calculated with a geometric integral. So if you have a rectangle or a triangle or any shape that we can just calculate the area under the curve, we're going to go ahead and do that for step 3. All right, so taking a look at our process here, I see one easy work. That's going to be the work from 3 to 1. That is a rectangle here. So we can calculate that by P times delta V, or minus P times delta V. I like to break it up, so I do the sign first and then the magnitude second. Don't have to carry as many minus signs around that way. And so I'll calculate the absolute value of the work here, and we've already assigned from 3 to 1 that it's going to be a plus sign, because we've already thought about whether we're smashing the gas or not. All right, so in order to calculate the work from 3 to 1, it's just the area of that rectangle. Which is going to be equal to P1, which is the same as P3, so I'm just going to call it P1, times delta V, which is going to be V3 minus V1. V1 is given to be 1,000 cubic centimeters. Okay, well, we need to figure out what P3 is. So we got to fall back now on the ideal gas law and figure out our state variables at each point. So for this is not as rigorous, but it might be useful to create a PVT table in order to store our values for PV and T at each of the 3 points. We don't have to fill this out with all its points unless we need them, but let's just go ahead and construct it. So we're going to have P, V, and T. And may space this out a little bit more. Sorry about that. P, V, and T. And these are for each state, so 1, 2, and 3, not for processes, right? These are the stopped points, the dots, opposed to the lines that connect them. And so what do we have? We have at well, we have none of them completely, but we have a temperature 133 degrees Celsius and a volume 1,000 cubic centimeters. Those are both at P1. So I'm going to write them in useful units. So 1,000 cubic centimeters is going to be 1,000 times 10. Anybody know how many cubic centimeters there are in a cubic meter? Not 100. Not 1,000. You know what it is? Well, if 1 meter is equal to 100 centimeters, which is equal to 10 to the 2 centimeters, then 1 meter cubed is equal to 10 to the 6 cubic centimeters. A million cubic centimeters. So, that is 100 in one direction and 100 in the other direction. That is a layer of 10,000 cubic centimeters. And then we have to stack 100 of those layers, and 100 layers of 10,000 is, in fact, 1 million. So I'm going to write our volume here as not 1,000 cubic centimeters, but I'm going to put it in SI units. And so I'm going to write this as 1,000 times 10 to the minus 6 meters, cubic meters. So a cubic centimeter is 10 to the minus 6 cubic meter. All right. What else? So the temperature, it's 133 degrees C. And we'll hold off on this for right now. Let's go ahead and calculate what P is going to be. We know that P is 5 times, P is just P1, an unknown value. All right. What are we looking for here? I guess we need P in order to calculate this thing. We also need to know what V3 is going to be. So let's calculate, let's go ahead and calculate P from the ideal gas law without any comparisons, but we're going to need to know the number of moles to do that. So we have P1V1 is equal to nRT1, where T1 is 133 degrees C, and which is equal to, we got to add 273 to that, 406 Kelvin. So I'm going to go ahead and put that in the box. I'm going to write this a little bit bigger so you can see it. I don't know why I zoomed in so much. Great. So, we're going to need the number of moles. We have 120 milligrams of helium, which I'm going to write actually not as milligrams, but 0.120 grams of helium. And we know that there are, looking at the periodic table, we see that helium has a molar mass of 4. So there are 4 grams in 1 mole of helium. And so if we take 120 and divide by 4, we get 0.030 moles of helium gas. All right, we're looking for P1 is what we're on a mission to find here. So P1 is going to be equal to nRT1 over V1. Which is going to be equal to 0.030 moles times R, which is 8.31 joules per mole Kelvin, times T1, which we just calculated to be 406 Kelvin, divided by V1, which is 1,000 cubic centimeters. Oh, sorry. 1,000 times 10 to the minus 6 cubic meters. Can't avoid making my mistakes even when I try. All right, there we go. So now we have SI units for everything, so we can just punch this into our calculator. And when we do that, we get 0.3 times 8.31. Oops. Sorry. Those keys do something in that app. Let's try that again. 0.03 times 8.31 times 406 divided by 1,000 e to the minus 6. 101,216 pascals. Maybe recognize this as being very close to 1 atmosphere. Food for thought. I don't know, it's not useful to us, but it is 101,216 pascals. So we can fill that into our table here. I'm just going to add pascals to the top here because those are going to be the implied unit. We know the pressure increases by a factor of 5 when we go to state 2, because that is given on our chart here. We have a 5 P1 here. So let's go ahead and fill that in our PVT chart because it will probably be useful for us. 506,000 79. The volume is the same at that point because it's a constant volume process, and we don't know the temperature. Let's go ahead and calculate that while we're here. So for this, now we want to relate two states, so we're going to write down the ideal gas law twice. We start with P1 V1 equals nR T1. And we also have P2 V2 equals nR T2. What I like to do next is erase any subscripts on any quantities that don't change along the process. So going from 1 to 2, we have a vertical line, and that means the volume doesn't change. So there's not V1 and V2, there is just V. And we can drop a subscript here. Great. And now we can apply a substitution. P2 we know is 5 times P1. So we'll go ahead and drop that in there as well. And now what we want to do is put everything, and now we have P1 showing up on both sides, so I'm going to drop the subscript on that as well. Great. So now we want to move everything that doesn't have a subscript to one side of the equal sign. So P, V, N, and R are both related between these two equations. So let's go ahead and put those on one side of the equal sign. So we're going to get that T1 is equal to PV over NR. And in this equation, we're going to get that T2 is equal to 5PV over NR. And you'll see that PV over NR is just T1, so we end up with T2 is equal to 5 times T1. And T1 was 133 degrees Celsius, so 5 times 133 is, I pushed those buttons again. I can remember those. Do something. 5 times 133 is 665. Is that what our temperature is? No. This is where we have to use Kelvin. We got to use Kelvin because 5 times the temperature compared to what? The temperature of freezing water is at atmospheric pressure is not a physical truth, right? It is just happens to be here at 1 atmosphere. Water boils at 100 degrees C and it freezes at 0 degrees C. That's what the Celsius scale is based on, but absolute zero describes an absence of molecular motion. And so that is what we mean when we say 0 in terms of our temperature. So we need to convert to Kelvin first. We've already done that. 406 Kelvin times 5 works out to be, oh my goodness, 2030 Kelvin. Oops. All right, let's go ahead and add that to our chart. Great. Well, we're still trying to get V3. So we just got to keep trucking along here. I think we're going to need to fill this whole chart out. So now we can do this process here again where we relate the 2 points using the ideal gas law. So we want to write down the ideal gas law twice. Let's get some new paper here. So let's do it again. P2 V2 is equal to NR T2 and P3 V3 is equal to NR T3. Next up, we can remove any subscripts that appear on both for quantities that don't change. We have an isotherm that connects point 2 and point 3, meaning the temperature between 2 and 3 is what doesn't change. So we can go ahead and drop the subscript on T. We also know that P3 is the same pressure as P1. So we can rewrite P3 as just P1. And we also know that P2 is 5 times P1. So we can rewrite this as 5 times P1. Maybe it would have been better if I did that on separate lines so we have a record of what we did. But we'll remove the subscripts to begin with, and then we'll rewrite on the next line here. So this is going to be 5 P1 times V2 is equal to nRT. And P3 is just P1 times V3 is equal to nRT. Great. Now we're in a good position to put everything that doesn't have a subscript on one side of the equal sign because it's already been done for us. nRT is what shows up on the right-hand side of both of these. So we're going to end up with, I guess we have a P1 that shows up in both of them as well. whichever. We'll just write down 5. We'll just keep it as it is, and we'll write down 5p1 times v2. That's this equation here, is going to be equal to p1 times v3, because they're equal on the right-hand side. Now the p1s cancel regardless, so let's just drop those now. And we end up with v3 is equal to 5 times the value of v2. Great. Back to our chart. Now we have a 5,000 times 10 to the minus 6 cubic meters for state 3. And the temperature is the same because it's an isothermal relationship. And the pressure is the same as at point 1. Great. Well, now we should have all of the information that we need to complete the rest of the first law table, which was our goal here. And we were trying to calculate P times delta V, which is this expression here. I will put the absolute value of the work here because I did drop the minus sign that goes there if we're strictly talking about W. Don't want to make that mistake. So if I put some absolute value signs around there, we can omit it because we already took care of the sign when we sat at the beginning and filled out the sign part of the table. All right, so that means this is going to be equal to P, which is 101,216. Is that right? Yeah, 216 pascals times V3, which was 5,000 times 10 to the minus 6 cubic meters, times, or minus V1, which is 1,000 times 10 to the minus 6 cubic meters. So that's 4,000 times 10 to the minus 6 cubic meters times our 101,216 Pascal. Okay, let's see if I can do this. There we go. 10216 times 4,000 e to the minus 6 is 405 joules. So that is from 3 to 1, and that is compressing the gas. So it is going to be 405 joules. Now, let's talk about the signs for a moment. We saved ourselves a big favor by figuring out it was the minus sign was there to begin with, that it was a plus sign because we're smashing the gas. But really, delta V should be V final minus V initial, so I should have done this as V1 minus V3, and then we should have had a minus sign out in front because the work is minus the area under the curve. But you see, by breaking it into two steps, sign first and then magnitude, we avoid a lot of pitfalls that we can make in terms of, ordering the states in the wrong order. Like I did here, I did V initial minus V final. That's not going to work for us if we're trying to retain the sign from the equation. So strictly speaking, since we're recording this video, I can just add a little more detail here. The work is defined for an isobaric process. Let me give myself a little more room. Thanks for bearing with me here. Work isobaric is given on our equation sheet, and we calculated it to be minus P times delta V, which is going to be equal to minus P times V final minus V initial, which in this case would be minus P times P, or V final was state 1 minus V3, which was state 2. And so you can see we do immediately end up getting a minus sign because this ends up being 1,000 cubic centimeters minus 5,000 cubic centimeters, which is a minus 4,000 and the minus out front. So we do get a net positive, but I think there's plenty of room for mistake there. And if we do the sign first and then the magnitude, that you can stay out of trouble there. All right, so this is 405 joules here. Great. And any more easy work? No, 2 to 3 is an integral because it is an isothermal process. Step 4, I would say what you want to do next is calculate, running out of room here, write it over here. Step 4 is going to be to calculate delta E thermal, because it has just one equation form, and it's a pretty simple equation to use. We have that delta E thermal for all processes is going to be equal to NCV delta T. And so we know the change in temperature between state 1 and state 2. And so we can go ahead and calculate what the change in the thermal energy is going to be. So the change in the thermal energy from 1 to 2 is going to be equal to the number of moles, which is 0.30, I think I may have said that wrong, times CV. Now this is on our equation sheet. We can go ahead and pull that up. So we have CV for monatomic and CV for diatomic. Helium is not He2, it's just He, so it's monatomic, so we're going to use 12.5 joules per mole Kelvin. Just did not give myself enough room yet again. It's my first time doing this. Never taught this before. It's not true. All right, so zoom in and write a little bit smaller. So we have delta E thermal from 1 to 2. It's going to be NCV delta T, which is 0.030 moles, times CV, which we said was 12.5 joules per mole Kelvin, times delta T, which is going to be T final minus T initial. T final in this case was our 2030 Kelvin minus T initial, which was 406 Kelvin. So we see then that as we go from state 1 to state 2, we have, calculate the number of joules here, 0.030 times 12.5 times 2030 minus 406. Got to put some parentheses in here. And I get 609 joules from state 1 to state 2. All right, we can add that now to our table. Now, since the sum of the thermal energy around the loop is equal to 0, we immediately get that this has to be minus 609 joules here in box number 2, and box down here 3 to 1. And now that we have box 3 to 1, we can also get the number of the heat from 3 to 1 because we have Q plus W equals delta E thermal across the row. So this is 405 minus 609. So this is like a little bit like Sudoku, right? I call this thermodynamic Sudoku or first law Sudoku because once you start to get these values together, we end up with a the other ones fall into place. So I get 1014. So 1014, minus negative 1014. 405 joules minus 1014 joules is equal to negative 609 joules. That's correct. And note that we're saved here by the fact that we pre-did the signs, right? So many opportunities to screw up the signs here in terms of what is the sign of Q and what is the sign of delta E thermal in each of these. And since we did the signs ahead of time, we're avoiding those pitfalls. Let me write this just to be a little clearer with the sign in situ. Okay, now another thing we can do is write all joules up here so we don't have to carry these J's around in every box, but we do have to make some note of the units. All right, so unfortunately in this particular problem, we need to do a calculator equation, which would be the work, which is a natural log. So that requires a calculator for the isothermal process, or we could calculate Q. But we have not talked about Q yet, so how to calculate Q directly. That is the least good solution oftentimes because there's different equations for different processes and it's easy to make mistakes. So I'm going to go ahead and calculate the work from 2 to 3. And for that, we're going to need the the isothermal work, which is also on our equation sheet. Although the derivation for it was straightforward, it's just minus the integral of the first law problem, assuming that the ideal gas equation, assuming that T is constant. We had something like 1 over V, and then we integrate it and we get the natural log. But we'll just use the expression here on the equation sheet. W isothermal is equal to minus nRT times the natural log of V final over V initial. And so the final volume is state 3, which is at the bottom of the hill. So that's going to be our 1,000 cubic centimeters. And we're going to have our 5,000 cubic centimeters for the initial. So this is going to be equal to minus 0.030 moles times R, which is 8.31 joules per mole Kelvin, times T, which is constant at 2030 along that isotherm. And then we have times the natural log of a fifth, 1 over 5. All right. So we're going to plug that into our calculator. Very last one here, minus 0.030 times 8.31 times 2030 times the natural log of 1/5. And I get 815 joules for that. And that's going to be a positive 815 joules. Let's make sure that that agrees with our, oh, I have a minus sign there. What did I do wrong? Maybe I'm missing a parenthesis here in my calculator expression. I'm hoping that is the case. Okay, V final. Oh, the bigger volume is the final volume. Sheesh, my apologies here. V final is 5 times that of V initial. Once again, saved by the signs in the chart. So this is going to be a minus sign out front by the time we're done, and easy to make these mistakes. So let's go ahead and plug that in. We have minus 815 joules here. So we're going to have a net negative work, which is what we expect because it's a clockwise process. The sum of the work down here that goes at the bottom is going to be equal to 410 joules. Right? That makes sense. It's also negative, which we already discussed, and we can complete across the rows. So Q here is going to be plus 815 joules for the isothermal process. And I guess a while ago we could have gotten Q from 1 to 2 because we have 0 work and 609 joules as the change in the thermal energy, so that all comes from heat. Great. That is the first law table. It is a long process, but reviewing the steps one more time. Step 1, we identify the 0. Step 2, we fill out all the signs in the boxes that we can. Step 3, we calculate the easy work. And then step 4, you do what you got to do to get the rest done. For now, our only tool that we have left is to calculate the change in the thermal energy using NCV delta T. All right, guys, that's all I have for you for this example problem. Tune into another video for more, and good luck in your preparations. Thanks a lot.